Good morning, folks. I think it's time to get started. Hope you all had a good long weekend. We are back in action. I hope nobody tried to go to the classroom, but you'll find out soon enough that we're on Zoom today. We do have homework due tomorrow as usual, and quiz on Friday as always. I don't have anything else, any other announcements to make? I don't think so. Let's get down to it. So this is what I said at the very end last time. The derivative of an exponential function with some other base. So b to the power x, where b is some positive number. You only do this for positive values of b. The derivative of b to the x is b to the x times ln of b. Where this comes from, remember, is the definition of b to the x is e to the x ln b. And so when you take the derivative of that on both sides, well, if you just take the derivative of this, what you get is e to the x ln b, which is the, because it's a power of e, you get the same thing again, and then you have to multiply times derivative of the inside of the exponent. The exponent is x times the constant ln b, so when you take the derivative of that, the x kind of goes away and you just get that constant ln b. And this, of course, is b to the x. That's the definition of b to the x. So it's b to the x ln b. You don't really have to remember that little why it's true. I would suggest just remembering what's in the box there. The derivative of b to the power x is b to the x ln b. This is an exponential function with a different base, and these are actually very useful in the real world. In a little bit I want to tell you about. I actually used an exponential function with a different base in my real life. This is amazing. I don't usually use advanced mathematics in my real life. In my real life, I have to add things, sometimes multiply things, but really very rarely do I do anything fancier than that. But that's a little something to look forward to. Anyway, I thought let's just do a couple examples of making use of this derivative formula. It's pretty straightforward to use. So if you have something like derivative of 10 to the x, you get 10 to the x times the natural log of 10, right? That's just using the formula directly. And you know, if you cared about this in your real life, you would just use your calculator to plug in that natural log of 10. More often, or more interesting examples would be when it's not just x up top. So how about 4 to the power 3x squared minus 2x? We're going to have to use the chain rule here. So we're going to use the formula in the box. Sorry, I'll just write it again here. Derivative b to the x is b to the x ln b. All right. So we're going to use that formula where b is 4. And instead of x, I have that extra stuff, 3x squared minus 2x. So it's going to be just plugging into this formula directly. On the right side, you get b to the x again, which is going to be 4 to the 3x squared minus 2x again. And then times ln b, which in this case is the natural log of 4. So there I just plug directly into the formula. This is not the end though, because I have to do the chain rule. So this right here is the derivative of the exponential part. And then I got to do times derivative of the inside. By inside, I mean the inside of the exponent. And the exponent being 3x squared minus 2x. What are you going to get for the derivative of that?
6x minus 2.
6x minus 2. Great. And it better be in parentheses like this. Because of that minus 2 in there, it means that really if you cared to simplify this, you would have to distribute. So you need the parentheses there. If you leave out the parentheses, it's not quite right. All right, all you parentheses haters, make sure you put the parentheses in there. Any thoughts about that? Questions? Here's another one. How about derivative of 8 to the power negative x squared? Same idea. We begin by doing the formula directly, which is when you see derivative of b to the x, you get b to the x ln b, first of all. So this is going to be 8 to the minus x squared again, times ln of 8. That's the derivative of the exponential part. And then separately, I multiply times the derivative of the inside of the exponent, which in this case is times negative 2x, like that. And that's how we do it, the derivative of an exponential function. All right. This, in that one, you don't need the parentheses, although it's not wrong if you put them there, but they're not necessary this time because there's no distributing that needs to happen. All right. Any questions about those? I think it's pretty straightforward. Here's a trick. How about this? What if I had something like this? 5 times 3 x squared. Is this a trick? I don't know. What should I do with that? There's kind of an easy way and a hard way. Is it too early in the morning for a weird example? Yes?
Do you have to multiply those out before you expand the terms before you do your derivative there?
Yeah, multiply it before you do the derivative. This is like, it looks weird, but actually it's not really weird. What you just multiply 5 times 3 is 15. So really this is derivative of 15 to the power x squared. And then it's just like the one before, right? This is needlessly complicated looking. It's really not complicated at all. So we get 15 to the x squared times ln 15 times 2x, right? That's all there is to it. You gotta multiply it inside there. It looks weird, but it's really not all that interesting. All right, great. I think that'll do for these. Okay, along with that derivative formula, which I will write again, just to refresh your memory, derivative of b to the x is b to the x times ln b. It says when you take the derivative of an exponential, you always have to multiply times the natural log of the base, all right? For the same reasons, if you do the antiderivative, you have to divide by the natural log of the base. So together with this, there's a formula for the antiderivative of b to the x. And it involves dividing by the natural log of the base. So what you get is this, b to the x over ln b, like so. All right, and this is the corresponding formula for the antiderivative. So these really, they sort of go together. The derivative, you multiply by the natural log of the base, and the antiderivative, you got to divide. No big whoop. All right. So the antiderivative formula, just to do a couple examples of that. I mean, if it's just like this, then this is easy enough. You just do it just plugging directly into the formula there. With b is 3, I get 3 to the x divided by ln 3. All right. That's not terribly interesting. I just plug immediately into the formula. This is more interesting when you have to do a u substitution at the same time. Let's just try a simple one like that. How about integral of, this will be wild, cosine of x times 5 to the power sine of x dx. All right. This is a little wild and crazy. You better do a u substitution just because that's really the only fancy trick that we know of to handle a weird function like this. Would anyone like to suggest what to use for the u?
Say sine.
Yeah, how about sine of x? You know, generally you want to choose the u to be something which is on the inside of something, and in this case, choosing the inside of the exponent is a good idea. So u is sine of x, and that means the du would be the derivative of sine, which is cosine. So this is cosine x, dx, of course. And then we plug the business in here. What do we get? Integral cosine x times 5 to the u dx. I just stuck the u in where it goes. And then, as I like to do, I'll write the u stuff sort of at the beginning, and then everything that's left over is cosine x dx. And I made this one up so that it would work pretty easily. That cosine x dx is du. So this is just integral 5 to the u du. And now we can use our integration formula, right? Integral of just use this formula directly. We have 5 to the power u, so it becomes 5 to the u divided by ln 5. So this guy becomes 5 to the u over natural log 5 plus c. And then the last step, as always, we put the x's back in. So my final answer is 5 to the power sine x divided by ln 5 plus c. There you go. So this is the integral of an exponential function, different from e to the x. If it's e to the x, it's a little easier. You don't have to handle that extra ln b thing. All right, any questions about that? Thoughts? All right, great. This is all I want to say for now about exponential functions with a different base. Although, like I said, I want to do a real-world example. But actually, the real-world example that I'm referring to also involves a log with a different base. And that's a little more interesting to talk about. So let's talk about logarithms with other bases. All right. The natural log is the, we call it the natural log, but another way you could describe it is the log with base e, because it is the inverse of e to the x, right? If y equals e to the x, then ln of y equals x. This, remember, is what it means, that e to the x is the inverse of the natural log of x. All right. The other logarithms are defined as the inverses of the other exponential functions. So if y equals something else, b to the power x, the inverse is called, well, we write it this way, log with base b of x, or log with base b of y, whatever you want to call the variable. Log with base b of x. This is, it's the inverse of b to the power x. All right, that's the definition of what log base b of x means. So if y equal b to the x, then log with base b of y equals x. This is the definition of what the other logarithms are. So we have the natural log, which corresponds to e to the x. It is the inverse of e to the x. And then we have the other logarithms, which are the inverse of the other exponential functions. All right? These are the other logarithms. It is a little confusing to think about, but if you understand the definition well enough, you can actually do these logarithms by hand. I mean, without a calculator, at least some of them, if you get lucky. So let's try to do some examples where we find the logs by hand. For example, what is log base 2 of 8? Can we do this by hand? It's actually mostly in your head. You just have to think properly about this. So the idea is, if I write log base 2 of 8 equals something, this means 2 to the power equals 8, right? I'm rewriting this as if it were an exponent. So we have, we did this a little bit last time. You can, whenever you have something written in terms of logs, you can convert that into an equivalent thing, which is written in terms of exponents. And then you can just guess the answer here. Can anyone say, what should the exponent be in order to make that true? You can show me the fingers if you want. Or go ahead. 3. Yes, the answer is 3. East Coast. 2 to the third equals 8, right? So, you know, this is 3 in this example. So that means that log base 2 of 8 equals 3, all right? If your friend asks you, like, what does log base 2 even mean? It means what is the exponent which is required so that 2 to some exponent equals whatever the number is inside the log. It is a little confusing, but hopefully you can get used to it. How about, you know, log base 4 of 16? What do you say? Someone can shout it out. Or give me the fingers if you want. Yeah, so what is log base 4 of 16? 2, right? The answer is 2. Why is it 2? It's because since 4 to the power 2 equals 16. This is what you have to think about when you see log base 4 of 16. The question in your mind should be, what power do I need to make 4 to the power whatever equal 16? All right? How about this? Here's a little tricky one. Log base 4 of 1 over 16. All right? This one, you need to be thinking about 4 to what power is 1 over 16. Any masters of exponents out there? You have to imagine. How could you possibly get this kind of fraction? Say it again.
-2.
Yeah, -2. Remember what the way you get a fraction from an exponent is by using negative exponents, right? Negative power means 1 over whatever the thing is to that same power. So 4 to what power is 1 over 16? The answer is -2. Log base 4 of 1 over 16 is -2. If you want some fraction to be the answer when you do the exponent, you better use a negative power. All right. How about, say, log base 7 of 1? This means 7 to what power equals 1? What do you say?
Zero.
Yeah, 0. 7 to the 0 power equals 1, right? This is since 7 to the power 0 equals 1. Actually, anything to the power 0 equals 1, right? That's just true for, this is not special about 7. So in fact, I'll say actually, and this is a basic fact about any logarithms, log with base b of 1 equals 0 for any b. This is because anything to the 0 power equals 1. And so no matter what the base is, the log of 1 is always equal to 0. Right. Great. So it is possible to do logarithms in your head sometimes. If you get lucky. Like if I just choose numbers at random, then there's no way to do that. Like if I ask you to do, say, what is log base 5 of 10? Then really what I'm asking, this looks like maybe you can do it, but actually you can't do this in your head, because what I'm asking is 5 to what power equals 10? And the answer is, I don't know. I mean, 5 to the 1 is 5. 5 to the 2 is 25. It doesn't hit 10 by any number that I know of. So actually the true answer to this problem is some kind of weird irrational number. But could I just say this is something between 1 and 2? I can say that because 5 to the 1 would be too small, but 5 to the 2 would be too big. So whatever this is, it's in between 1 and 2. But really you can't say much more than that without using your calculator. Obviously you can use your calculator to figure this out. All right. Boop, boop, boop. I feel like I'm missing a... No, this is all right. Okay, I think I'm ready for my real-world example. Can you believe it? I actually used logarithms and exponential functions in my real life. I hope you don't mind a little personal story about me. This is a medical scenario that I found myself in about maybe like 7 or 8 years ago. I found out that I have a genetic disorder called hemochromatosis. This is a any of you guys have a hemochromatosis also? No. All right, it's good. It's not a good thing to have, although it's really not a big deal. But hemochromatosis is a genetic disorder which is the result of a gene mutation which originally appeared as they've done, somehow the geneticists have studied this, and it seems that this mutation originally appeared in human beings in during the Middle Ages in Northern Europe. So this genetic disorder is only it only affects Northern European white people because you have to be a descendant of this mutated gene. So Northern European white people, that means like Fairfield University could be ground zero for hemochromatosis. I never knew how truly white I was until I found out that I have hemochromatosis. And in fact, so it's a recessive gene trait, which means that in order to actually get it, if it's like you can be a carrier who doesn't have the condition. In order to actually have hemochromatosis, you need to both of your parents need to be a carrier, and you need to inherit the bad gene from both of your parents. It's one of those things.
Professor, you'd use like a Punnett square to figure that out, right?
Yeah, something like that. Yeah. So it means, for example, that my kids have some. My kids will definitely be carriers of the recessive trait, but they probably will not actually have it unless my wife also happens to be a carrier of the recessive trait. And my wife is also similarly white, and so the existence of this in the population, about 1 in 40 white people are carriers of the recessive trait, which means if you sort of do the genetics, it means about 1 in 800 white people actually have the condition like me. So there's, I suppose there's a 1 in 40 chance that my wife is a carrier, and then if she really is, then my kids could get it, but it's not likely. Anyway, my parents, by some kind of cosmic coincidence, both of them actually have hemochromatosis also. So I was guaranteed to have it. It's like my parents were perfect for each other. They didn't know this until about like I said 7 or 8 years ago. Like my whole family found out that we all have it. I do, and my sister does, and both of my parents do. I have another sister actually who's adopted, and she does not have it because she's Korean. But anyway. The treatment, so what it is it causes, there's like a natural mechanism in your metabolism which causes iron to be flushed out of your body. And if you have hemochromatosis, this natural process which removes iron from your body is broken. So people with hemochromatosis build up iron in their body like over the course of your whole life. And it's actually not very harmful until you get old, which is why in the Middle Ages when this first arose, it wasn't harmful to people because they didn't live long enough. But now it's like you can have this your whole life, and then in your 60s, like your feet will turn orange because there's like it can actually make rust appear in your skin from the excess iron, and then it will like make your kidney fail and you will die because of it. But if you have the treatment, like if you know that you have it, it really doesn't hurt you because there is a treatment to remove iron from the blood, and this is where the exponential functions come in. So I must sort of artificially remove iron from my bloodstream. And the treatment, unfortunately, there's not like a pill that you can take that just like flushes iron out of your body. The only way to remove iron from your body, the iron is like free floating in your blood. Then the way to remove the iron from your body is to remove the blood from your body. This is the way it happens. So this is called therapeutic phlebotomy. This is removing of the blood. So, what you do if you have too much iron in your blood, you go somewhere as if you were like donating blood. They take a bag of blood out, and then, in my case, like right in front of my eyes, they unceremoniously dump this bag of blood into the garbage because it has too much iron in it to be useful for blood donation or whatever. So they take the blood out and then they just throw it away. And the idea is when some amount of blood is removed, the iron is removed along with it, and then your body will regenerate the blood but your body does not generate its own iron because iron is an element. Like, it cannot be created by your body. The only way iron gets into your body is when you eat things. So anyway, this is the scenario. When you do this phlebotomy, they take like a standard bag of blood out, and this removes, for sort of an adult male such as myself, the typical bag of blood that they take removes 10% of your blood. Right? This is not harmful. It just, you gotta eat some peanut butter crackers at the same time or something. So I do this. They take out 10% of your blood, and this automatically, I will say, i.e., this removes 10% of the iron. Right? I actually did this once. I was sitting in the chair. They're taking this blood out of me because I have too much iron in my blood. And right next to me, there was a lady in the chair sitting next to me. She was getting like IV dripped iron infusions because she didn't have enough iron in her blood. And I thought maybe there must be a better way to just hook me straight into this lady. We could save a step, but they didn't do that.
If you were a conducive blood type, do you think that would work, like theoretically?
I'm not a doctor. I do have a PhD, but not that kind. I don't know.
Doctor.
Yeah. So anyway, you do this, it removes 10% of the iron. Actually, women, hemochromatosis is less harmful to women because, as you may know, I don't need to educate you on this. Women have a natural process by which the body loses a certain amount of blood on a regular schedule, and this actually, for most women, this might make them iron deficient, but for women with hemochromatosis, it's helpful because it gets rid of some iron. Anyway, okay, so let's talk about the details. My own personal experience. When I first discovered that I had this, it's because my sister had some kind of blood test, like non-typical blood test, and they discovered that she had way too much iron in her blood, and then we all got this genetic test, and they found out that we all have it. Anyway, the actual measurement that they use to measure how much iron is in the blood. So this is blood iron is measured as what they call the Serum Ferritin level. Ferritin is like the particular form of iron that is floating around in, like, free floating in your blood. Iron, of course, is useful in building hemoglobin, and actually, iron. People with way too much iron in their blood are resistant to the bubonic plague, which is a good thing, I guess, for me. But this is why the mutation became prevalent in the Middle Ages, because it was actually helpful at that time when all kinds of white people were dying from the bubonic plague. So if the bubonic plague ever comes back, I'm your guy. I'll be in good shape. Anyway, the serum.
Did you see that bubonic plague popped up in like Montana this summer?
Yeah, it comes like every so often. Somebody gets it, but the bubonic plague is actually very easy to treat. Like, penicillin treats it immediately, so it's not really harmful anymore.
Yeah, it was like a squirrel, I think.
Oh, really? Yeah, it's kind of a surprise to me. It's surprising to me that it even exists anymore. But anyway, the serum ferritin level. So a healthy level is around 20, and the units for this is very small, nanograms per liter. This is a healthy level of serum ferritin. And when I was diagnosed, when I found out that I had this, so I found out when I was like in my 30s, so I had this thing for 30 years of iron building up in my body. Mine was 800, nanograms per liter, which is way higher than the healthy amount. And what if you this actually was not really harmful to me though. If you go your whole life, like it can cause organ failures. But even for me, even 30 years, getting this high was not. I had to have a bunch of tests, but all of my organs are fine. Anyway, so I went to my new blood doctor, and he said, all right, what we got to do, we do this phlebotomy thing. We just take the blood and do that over and over again. Every time you do that, it reduces the ferritin by a little bit. And naturally, I asked how many times we got to do that to get down to the healthy level. So, and this is the question I want to answer. So, how many phlebs? This is what the nurses call it. We're gonna phleb you. How many phlebs do I need to get to 20? All right, and the answer to this has to do with the fact that every time you do the phleb, it reduces the iron by 10%. All right, this is our assumption. Now, of course, medically, that's not exactly. It's not exactly going to be 10% every time, but that's more or less the way it works. Because 10% of the blood is being removed, that means 10% of the iron will be removed. So it drops 10% each time. So I can make a function. Let's call it like f of t is the ferritin level after t times, right? And I actually did this math, because I asked the doctor how often do we need to do this, and a doctor doesn't really have to do this math. They're just like, well, we'll just do it a bunch of times, and every time we do it, we check your level, and we just do it until you are at the healthy level. But I was interested in trying to predict this. So the ferritin level after t times. So we could say this immediately. F of 0 is 800, right? That's after doing it, not doing it at all. I would start it at 800. Anybody want to say what do we predict f of 1 is going to be? It's supposed to reduce by 10% every time.
720.
720, yeah. I think how we did that was, how did you do that?
I just took 10% of 800 and then subtracted.
Yeah, right. It would be 800 minus 80, which is 10% of 800, right? That's how you get 720. Okay, the next time, f of 2, we decrease it again. This time, I suppose we're going to decrease it by 72, which would be 10% of 720, right? So that would be, I did the math on this, 648. This is 720 minus 72. We subtract 10% every time, all right? What's a formula? I would like a formula. F of t equals some business in terms of t. Now, it's not clear how to do that as a formula. I think thinking of it as subtract 10% every time, that certainly makes sense, but it's actually not a very convenient way to think through if you're trying to translate this into a formula. Here's a better way to think. Instead of saying we remove 10%, how about we say instead we keep 90%, right? That's the same as remove 10%. So this 800 minus 80, another way to think of that would be 800 times 0.9, and it's the same, right? Removing 10% is the same as multiplying everything by 90%, all right? And that is actually easier to translate into a formula. So after f of 2, what we get is we multiply by 0.9 again. In fact, you could write it this way, 800 times 0.9 to the power 2, right? Because it comes from the previous value, and then you multiply 0.9 again. So f of, what's f of 3? It is whatever this is, 800 times 0.9 to the power 3, right? This is, it is an exponential function, isn't it? F of t, so what is f of t in general? It's going to be 800 times 0.9 to the power t. All right. Actually, as soon as I found out that I had this, and I This will tell you something about the kind of person I am. I read about the phlebotomy treatment, how it works. I immediately thought to myself, oh, this would make a good example in my calculus class of an exponential function of a different base and how you have to use a logarithm to answer basic questions about this. So the question is, when do we get to f of t equal 20, right? This was the question. How, like, for which t will you actually get the ferritin level down to 20, which is what I said is the healthy level. How do we do that? Well, we just got to solve this thing, set this thing equal to 20, right? 800 times 0.9 to the power t equals 20, and then I want to solve for t. All right. And now you will see t is inside the exponent. So in order to solve for t inside the exponent, I'm going to use a logarithm. This is the classic scenario where you want to use a log to do something. Remember, I'm going to use the basic rule about log of a to the power r equals r times ln a, right? Sorry, it's under my picture. This is the way in which you move. This rule here allows you to move whatever was inside the exponent and turn it into a coefficient, which then lets you solve for it on one side of the equation. So I'm going to do that over here. Take the natural log on both sides is what you got to do. But actually, I'm not going to do it immediately. When I take the log, it needs to be just the log of the part with the exponent. This 800 I don't want over there, so I'm going to divide the 800 first. So 0.9 to the power t equals 20 over 800, right? Which I guess is 1 over 40 if you like. It doesn't really matter. But now I can take the log on both sides. So I go ln 0.9 to the power t equals ln of 1 over 40. Move the exponent down to the front. So t to the ln 0.9 equals ln of 1 over 40. And then I can solve for t, right? So it's ln 1 over 40 divided by ln of 0.9. And this, my friends, you can just type into your calculator and get the answer. The answer is, so I put this in my calculator, I got 35.01 ... So that means I need to do it 35 times to get to the healthy level. And when I first met with my doctor, he said, let's do this every 2 weeks for a year. And then see how you look. And so that was the plan, and it wasn't quite enough. Yeah, question?
Wouldn't that not technically work? Because wouldn't the iron replenish over time, so it wouldn't be 35 times?
Yeah, right. So this whole sort of mathematical model here doesn't account for the fact that my body continues to accumulate iron during the in-between times. So yeah, it is a fact that you have to do it more than that, and also this is not a thing that you just sort of do all at once and then you're better forever. Like I have to go every I think I do it every 4 months now to like kind of maintain my my baseline level. Yeah, it has been suggested that sometimes people tell me like, oh, so you don't eat iron then because it's like bad for you, and it is kind of bad for me to eat iron, but really there is no it's hard to avoid iron because iron is in all plant and animal foods, and so there's not really a healthy way to cut iron out of your diet. So I eat it and then I bleed it. That's what we say. If you eat it, you must bleed it. I really do like the frosted mini wheats. I have the mini wheats every morning for breakfast. I don't know if you've ever noticed, but the mini wheats are fortified with iron, which is not good for me, but I can't quit the mini wheats. All right, so that's my real life example. I hope that was interesting. I used logarithms in my real life. This is actually, I believe, the only time I've used logarithms in my real life. It's not a thing that comes up very often, but it does come up in science and physics or whatever. These kinds of things happen all the time. anytime you have an exponential formula for something, which does happen very much in the real world. All right. Any thoughts about that? All right, let's move along then. I want to say just a few more things about logarithms and ease and all of that, and then we're going to move on to something completely different. I think we'll get done with this section today. A couple last properties about logarithms. So it is a fact that any, what? I wrote two A's. Any log, if you have seen logarithms at all, you probably saw this formula that I'm about to share with you. Any logarithm can be written in terms of the natural log. All right, and this is what I'm about to say is referred to as the change of base formula. If you have a log with a different base, there is a way to rewrite it only using the natural logarithm. And this is why, for instance, your calculator doesn't have buttons for every possible different base. You usually just have the natural logarithm, and sometimes you'll have a base 10 logarithm button. But it's because other bases, they can always be converted into the natural log. And here's the idea. So if, like I said before, if y equals log base b of x, then that means automatically that b to the power y equals x. This is rewriting the logarithmic formula as an exponent, all right? What we can do with this, if I do ln on both sides, it'll say the natural log b to the y equals the natural log of x. But then I can do, you know, our favorite trick with exponent inside of a log. This exponent here can come down front because that's the rule about logs. And then we can solve this for y. It says y equals natural log, what? Sorry, I changed the x into a y. This is an x over here. And this one too. The eraser, come on. Okay, ln x divided by ln b. But remember I started with y is log base b of x. So in conclusion, this says log base b of x is ln x divided by ln b. And this is what they call the change of base formula. It comes from just doing some simple manipulations of the logs. If you rewrite things and take some ln's on both sides, you can come up with this special formula here. Oops. This is called the change of base formula. And this, in this way, if you ever wanted to find some weird log on your calculator, even though your calculator only has a ln button, this is how you would do it. So to find something like what is log base 5 of 10, this is the one I said a few minutes ago. This is one that looks like maybe you can do it in your head, but actually you can't. I said it was something between 1 and 2. The way you would do this is you just use the change of base formula. This is equal to ln of 10 divided by ln of 5. And what's that? This you can type into your calculator and get something. Actually, I didn't do this ahead of time, but you could type that into your calculator easily, and you would get some answer. All right. I'll just put some scribbles there. Whatever the answer is, that's what the answer is. Okay? The change of base formula. It comes up fairly often. All right? Actually, we can use the change of base formula to find the derivative of the log. So use this to find the derivative of log base b of x. All right? Because you can just rewrite that log base b in terms of natural logs, and we already know how to find the derivative of natural logs. So this is the same as derivative of ln x over ln b, right? How do we do this derivative? You might worry that we have to do the quotient rule because that is a quotient inside of a derivative, but actually you don't have to do the quotient rule because the bottom there is a constant, right? The natural log of b, x is my variable, which means the bottom there is a constant. So we can actually just factor it out of the derivative entirely. This is 1 over ln b, derivative of natural log x, right? If you have a constant multiple, you can ignore it when you're doing the derivative. Just leave it in front of the answer. And then, anyone remember what is derivative of ln x? Yeah, 1 over x. I hope you remember that. And this is the formula for the derivative of the log with a different base. So I will write that again. Derivative of log with base b of x is, usually it's written this way, 1 over x ln b, which is the same as just a rearranged version of what I wrote just a moment ago. All right. So this is the derivative of the log with a different base. You get 1 over x ln b. We could do some example. I don't think we need to do examples. This is just the same. Maybe we'll do one. Just simple sort of log base 5 of x squared minus 2x. What's it going to be? You go 1 over x ln b. So the b in my case is 5, right? And instead of x, it's all that stuff inside the parentheses. So my answer is going to be 1 over, I'm doing this formula, right? But instead of x, I have all this stuff inside the parentheses. So it's 1 over the stuff inside the parentheses, x squared minus 2x. And then I got to put the ln b. b is 5, so ln 5 like that. And then I got to do the chain rule, as always. You know, when you're using one of these formulas, but it's not just x, it's some other stuff in here, you got to do the formula as written, and then you have to multiply times the derivative of what's on the inside. So the derivative of the inside is 2x minus 2, like that. So that's my derivative of the log. Alrighty. Any thoughts about that? Oh, great. Okay, I got one more thing to say in this section. You know, this what we've been talking about the past several times was logs and exponentials. One more thing to say about that, and then we're going to move on to something completely different. And that is something about the number e as a limit. The number e, you know, if you know, I hope when you're talking to your friends all the time about calculus, maybe you might mention to them. Everybody knows about the number pi. Pi is a great number, but there's another number that's just as great for different reasons. The number e. Your friends are likely to ask you immediately, what is the number e? Not like what are its digits, but like what does it mean? And this is a hard question to answer immediately. You could say e, it's the number for which the derivative of e to the x equals e to the x, or something like that. It turns out, actually, historically speaking, the number e was discovered because it appears as an important value of a limit, and I wanted to talk about that. The number e is has an important expression as a limit, and this is another way you can describe to somebody what exactly is the number e. Actually, once you know how to say it, it's very simple to write. E is the limit of this. Anyway, everybody knows. So we're not going to get to the limit right away, but everybody knows that e is the natural log of 1. All right. This is a property of. This is actually the definition of the number e we talked about a couple times ago. E is the number which is equal to the natural log of 1. This is not very helpful to explain to your friends what the number e is. They say, how do you get e? Well, e is the ln of 1. And then it will say, what is ln? And you'll say, that's another more complicated thing to explain. But anyway, e is the natural log of 1. And of course, everybody knows, we just said a moment ago, the derivative of the natural log of x equals 1. What? 1 over x. 1 over x, all right? So that means if f of x is the natural log of x, check it out. I'm going to write the definition of the derivative. This is something that we are not going to do perhaps ever again in this class, and this is something that you learned once to do, but then you more or less immediately learned how to do the derivative in easier ways. But I hope you remember at least that there is a formula like this. The derivative f prime of 1 is the limit as h goes to 0, f of 1 plus h minus f of 1 over h. Remember that thing? For like a few days, your calculus teacher made you find derivatives using this formula. And those were not good days. You had to do a whole lot of nonsense to get a very simple formula, things which you can do in a matter of seconds once you know how to find the derivative, but yeah, with other means. But anyway, this formula will come in handy just for the purposes of what I'm trying to say just for now about the number e. Can we simplify this? On the right-hand side, I'm going to say this is lim h goes to 0. What can we do inside up there? F of 1 plus h, I guess I just have to write as natural log 1 plus h. Minus f of 1, that will be natural log of 1, because remember, I'm using f of x equal ln x as my function, divided by h. What can I do about the left-hand side? Actually, f prime of 1, can anybody tell me what is f prime of 1? Where you can use the fact here that you know the derivative is 1 over x. What do you think? Is this too far out? F of x is ln x. What would you say f prime of 1 is? You know the derivative of ln x is 1 over x, right? Oops. I think, you know, f prime of x is 1 over x, isn't it? This is the derivative of the natural log. And so what is f prime of 1? It is 1 over 1, which is 1, right? Which is 1 over here. We know that the answer is going to have to equal 1, all right? This is a little weird because usually when you use this formula, it's because you don't know what the derivative is. But in this case, we already know what the derivative is. So we can use this. We can use this version of the derivative while also using this formula on the other side. Anyway, this limit on the right side equals 1. That's all I'm saying, right? This we can simplify a very little bit by, we can say ln of 1 is... what did I say before? I wrote e equals ln 1. Sorry, that's not, I messed that. Ln of 1 is 0, right? What I meant to say is ln of e equals 1. Can you scribble that out? I hope that you should have had some bad feeling when I said that. I should have had some bad feeling when I said that. Ln of e equals 1 is what I meant to write. The natural log of 1 is 0. We said that that's a basic property of the natural log. What's special about the number e? It is the number whose natural log equals 1. Sorry about that. So when we simplify down here, the ln1, when you see it inside there, that's 0. So this is equal to lim h goes to 0 of... Can I write it this way instead? Instead of divided by h, I'm going to write it as 1 over h times natural log 1 plus h. All right, the ln1 is 0, so that goes away. And then instead of dividing by h, I'll write it as times 1 over h. And then here's a non-obvious step. Left side is still equal 1. This over here, I'm going to use the old rule about exponents of natural logs. Usually we use this rule to take the exponent out front, but you can also shove a coefficient into the exponent. This will say lim h goes to 0, natural log of 1 plus h to the power 1 over h. Usually we use that rule to take the power out of a log, but of course you can do it both ways if you want to. Usually you don't want to, but here's one special example where you do want to take the coefficient and put it into the exponent. All right. And now this is almost done. I'm going to do e's on both sides. So on the left it will say e to the 1, and on the right it will say e to this whole thing here. Lim h goes to 0, ln 1 plus h to the 1 over h. Get too many parentheses there. All right. When I have the limit on the inside there, that's the same as if I were to take the limit out. On the left, you just get e. On the right, I'm going to move this limit down here because the limit only deals with h's, and the e part outside has nothing to do with h's. E to the power ln 1 plus h to the 1 over h. And finally, the e and the ln will sort of cancel because e to the ln of something is equal to just whatever the something is. So this is really the end of what I'm writing here. Lim h goes to 0, 1 plus h to the power 1 over h. And this is the description of e as a limit of something. I'm just going to write that again. And usually this is written with like x's or something. Limit as x goes to 0 of 1 plus x to the power 1 over x. That limit on the right side equals e. It's a true fact. And if you replace x by, if we use n equals 1 over x, the way this looks is this. Lim n goes to infinity. 1 plus 1 over n to the power n. This is actually the way in which the number e was first studied by mathematicians. And the reason this is important is because this formula, I don't know if you ever, we're not going to get into the details of this really, but this formula appears naturally when computing compound interest. If you've ever, probably you did some examples like this in high school once or something. Formulas involving compound interest, they look like that. The formula typically looks something like 1 plus r over t to the power, I don't know, nt, where r is the interest rate, t is the time, and n is the number of compoundings per time period. You may have seen this formula before. Anyway, that formula is apart from this r right here is the same as this formula right here. And people noticed that if you do more and more compounding, it doesn't actually make your interest go to infinity. It makes your interest go to some special number. You could think of this as letting the number of interest compoundings go to infinity, but it doesn't give you infinite money if you do that. You just get it sort of stabilizes at a particular value, which is the number e. This was the first discovery of the number e, and then you know, it was sort of after that the connection to logarithms was made, or the idea that doing a logarithm with this as the base would be useful. All right. This is my description of the number e sort of from a more historical point of view. And this is something that you could easily explain to anybody who really wants to know what exactly is the definition of the number e. You can say this is how you get e. If you wanted to like approximate e, say using your calculator, you could do something like 1 over 1 plus 1,000 to the power 1,000. This is approximately equal to e, right? You use some really big value for n there, and you'll get a number which is close to e. All right, this is the end of what I wanted to say about logarithms and exponential functions. Any lingering questions? I think we've said everything there is to say about logarithms and exponential functions. All right. There are properties, one thing that I didn't say, there are properties of the logs with other bases. They're the same properties you get from the natural log, so I didn't bother to write these, but there are things like this. these are true for all logs, not just the not just the natural log, but all those properties for the natural log. They are also true for all of the other logs. I'll just say, etc. Come on now, etc. All right. This property, by the way, is interesting in that this property is the mathematical basis for the operation of the slide rule. You ever heard of the slide rule? It was an old-timey mathematical instrument that is used for multiplying numbers, and it works according to logarithms. Because of this rule is why the slide rule works, but we're not going to get into that. All right, I think we're ready to move on to the next section. So the next section is still in the general category of inverses, which is really what this whole section chapter in the book, chapter 6, is about, inverses. This reminds me, actually, I had something to say about the homework assignment. I hope you've had a chance to check it out. But first of all, remember that there are like two parallel universes of sections in chapter 6. There's the ones without the stars and the ones with the stars. Ours, you should be using the ones with the stars. I wrote that in the assignment. And also, I always said that for our textbook, you could buy the new edition or the older edition, the 7th edition or the 8th. The newest one is the 8th. The previous one is the 7th. This week on the homework, there is one question which has, it's the same question, but it has a different number in the two different editions. So it's something like number 86 in the old version and number 88 in the new version. So when you see that on the assignment, what it means is check to see which version you have. If you have the newer one, you do that number. If you have the old one, you do that number. I hope that's not confusing. Let me know if you're confused. All right, great. We got about 10 minutes remaining. I think that's enough to give a little sort of brief start to the next section. The next section, and this is the last section dealing on the general theme of inverses, is about inverse trig functions. This is something that generally people don't do in high school, so this, and I'm pretty sure you didn't do it in your previous calculus class, so this may be new for everybody. I hope it's nice to have something new for everybody. Inverse trig functions. This, you've probably seen these buttons on your calculator. Your calculator probably has a button that says this. This is what we're talking about, that button on your calculator. This is called the inverse sine of x, or also sometimes called this, arc sine. That's a C, arc. Looks like an E again. Arc sine of x. These are synonyms. They are both referring to the same function. Sine of x. This, you know, when you see this, I'm going to say inverse sine, or the arc sine if you prefer. In our book, they always write it as inverse sine. It's meant to be the inverse of sine of x, although it's not quite so simple. But the reason why you would want to have an inverse of sine of x, for instance, this is in order to answer a question, to answer something like, if I want to maybe build a triangle which has a side on the bottom of 3 and the opposite side being 1, the question is, what angle should I use here to get a 3 on one side and a 1 on the other side? And this is a right triangle, of course. All right. What angle should it be? This is the classic scenario in which you want to use an inverse trig function. The reason you want an inverse trig function is because this whole picture here means you could write, in this case you wouldn't use the sine, you would use the tangent. The tan of x is 1/3, right? Because the tangent, I hope you all remember, is the opposite over the adjacent side. So in this triangle, the tangent of x is 1/3. So the question really becomes, what is the angle whose tangent equals 1/3? And now there are some angles for which you might be able to just remember that certain values equal certain other values, but actually none of this sort of angles that you're likely to remember on like the unit circle or whatever have a tangent equal to 1/3. So, but anyway, The answer, or the question that I'm asking is what x has tan x equal 1/3? And the answer is, well, we write it this way. The inverse tangent, or the arctangent of 1/3. And there is a button on your calculator which does that. So this is the purpose of these functions. This is why you would want to use these functions. It is to find some angle which has some tangent or sine or cosine, right? And there's even, you know, arccotangents or whatever. They're less useful. Okay. I said this is meant to be the inverse, but there is an issue. The major issue here is, I'll say, the big problem when it comes to treating this as an ordinary inverse is that these functions, sine, cosine, tan, they are not one-to-one. None of them are. They are not one-to-one. That means that in the traditional sense, these functions do not have inverses. You know, sine of x looks like this, right? Definitely not one-to-one. Remember, one-to-one means that if you can draw a horizontal line, it will only intersect the graph once. But here, actually, sine of x, horizontal line will intersect the graph infinitely many times. So it is definitely not one-to-one. It's like infinite to 1. This is sine of x. Cosine has the same issue. It's just sort of offset a little bit in the picture, right? This is cosine of x. And tangent, the graph of tan is a little weirder, but it also is not one-to-one. It has these vertical asymptotes. This is the graph of tan x. And it is also not one-to-one. None of these functions are one-to-one. So these functions, sine, cosine, tan, they do not have inverses. They have no inverse functions because they are not one-to-one. And so, but there is that button on your calculator. The button on your calculator is doing something that's kind of a little cheat to turn this into a useful thing which your calculator can do, but it's not a true inverse. These are still called the inverse trig functions, even though on some technical level they're not true inverse, and I'll try and explain that a bit more next time. But let's just talk about the inverse sine first of all. How do you invert a function which is not one-to-one? The answer is you can't find the inverse of a function which is not one-to-one, but we can do sort of the next best thing. For sine of x, we consider only a portion of the domain where it is one-to-one. This is our strategy to kind of get around the issue that the function is not one-to-one. We consider only the portion of the domain where it is one-to-one. So remember, sine of x looks like this. Not one-to-one, but if I focus only right here, within this box, it is one-to-one, all right? So we are going to ignore all the function values outside of this domain. We're going to consider only the domain. Now, because of the way sine works, this is pi over 2. I'm using radians, of course. This is minus pi over 2, right? So we consider only the domain from minus pi over 2 to pi over 2. And of course the range, if you care, is minus 1 to 1, right? And on that domain, we can take the inverse. But it's only of a piece of the function, but we can do the inverse of that piece of the function. So I'm going to redraw this kind of zoomed in a bit. So here's minus pi over 2 to pi over 2. And it goes down to minus 1 and up to 1. And the function sine of x looks like this. This is that piece of sine of x. Its domain is minus pi over 2 to pi over 2. And its range is minus 1 to 1. All right? And this little piece we can invert. So we can invert this piece. And only this piece. Because if you try to stretch beyond that piece, it's not one-to-one anymore and it doesn't work. And remember, the way to invert, I mean, at least by looking at the graph, is you reflect it around this diagonal line, right? When you're drawing this, don't draw the diagonal line like this from here to here, because that actually is not a 45-degree line, because this number pi over 2 is different from 1, right? Pi over 2 is actually quite a bit more than 1. It's like 1.5, more like 1.5. So anyway, my original diagonal line is more accurate. It should not go through the two endpoints of this function. And anyway, when I draw the inverse, I reflect this graph across that diagonal line, which means the x values, so the marked y values used to be 1 and minus 1. Those become marked x values now, minus 1 to 1. And what were those marked y values at minus pi over 2 to pi over 2? Sorry, they used to be x values, now they become y values. So minus pi over 2 to pi over 2. And the picture is the mirror image of that original curve. So the original curve looked kind of like an S, and what you're going to see now is sort of like a, I mean, it's again kind of like an S, but it's going upside down somehow. Like, it's like that. All right. If you don't look very closely, this will look like the same shape curve, but it's, the concavities are backwards somehow. All right. So in this one, this is called the inverse sine of x, or the arc sine. And its domain, so this is the domain of the arc sine, or the inverse sine of x, is minus 1 to 1. If you have your calculator with you, you can try to use this button. If you plug in 2, you'll get an error, because there is no such thing as inverse sine of 2. It's only from minus 1 to 1. And then the range is minus pi over 2 to pi over 2. If you're using radians, if you're using degrees, it would be negative 90 to positive 90 degrees. And unfortunately, this means you have to make sure your calculator is in radians mode. You know, we're pretty much always going to use radians in this class. The radians versus degrees will affect the answer of this button on your calculator, the inverse sine. All right. This is the inverse sine. Using similar tricks about taking only a piece of it, you can make an inverse cosine and an inverse tangent. But we will we'll discuss those things next time. I think that's enough for today. Unless, are any questions at the end here? No. All right. Great. I will see you all tomorrow at 9 in person, or on Zoom if you're not coming in person, but we will be in the classroom tomorrow. All right. See you then.
Thank you. See you tomorrow. Take care.